Okay, let's begin. There are three handouts. Graded set 1, the solutions to set 1, that's called handout number 8, and then homework assignment number 3, that's called handout number 7. These are available, of course, on the course website. And also I'm picking up homework set 2. So here people have dropped these off here. And our goal will be to grade them and have them back with solutions to you next Tuesday. By the way, next Tuesday is going to be fun. We're going to talk about the second law of thermodynamics and Boltzmann and Maxwell's breakthrough, where they were actually able to physically identify what pressure, temperature, and entropy was in thermodynamics. All this without seeing atoms. Said, if there were atoms, then this is how they would behave, and look, it explains everything. There's no mysterious substance called heat that somehow permeates bodies and you could squeeze out of it. That's nothing more than the kinetic energy of atoms. So that'll be fun, and we're going to get a lot of results free on Tuesday. And our point of view will be this. In the second law of thermodynamics, it says that entropy or chaos or randomness increases. Now, is this physics or is it mathematics? Well, mathematics, what is called the handmaiden of physics or something like that. But that's not what I mean. I mean, are things like the second law built in to the mathematics of simple stochastic processes like stationary processes and have nothing to do with the physics from which the stationary process arises. So by finding all those aspects of statistical mechanics and thermodynamics that are built into the math that have nothing to do with physics, we then free that part of the discussion from the physical part. All right. Last time we proved the AEP that says that probability of x1 through xn is equal with a dot over it is going to mean to first order in the exponent, spelled out in the text, 2 to the minus n h. So h equals the entropy of x1, and the xi's are independent, identically distributed. And this is called the AEP, the asymptotic equipartition of probability over the sequencers that are likely to occur. Quick review of that. Today's Markov processes stationarity and a number of things. We start really proving things. All right. Here's everything that can occur. Here's a small set A of things that are likely to occur. Probability of A is nearly 1. An element of A is nearly 2 to the minus nh. nearly and so on are rigorously defined, both in last lecture and in the text. And the size of A is roughly 2 to the nh. So these are the so-called typical sequencers. And a sequence will be called typical if this is true. We define it that way. And then if that's true, then we immediately get this result and that result. This result holds for n sufficiently large. That is, the probability is within epsilon of 1. And this is always true for all n. And this leads to data compression because it only takes nh bits to describe something in A, and A occurs with probability 1, near 1. And so we've compressed n log alphabet size bits into nh bits just by enumeration. Now, we'll actually solve the problem exactly with Huffman coding. We'll minimize the expected number of questions we need to determine x perfectly, and that'll turn out to be between h and h plus 1. Well, actually, for a sequence of length n, between nh and nh plus 1. Now, here's a funny thing about typical sequencers. You might want to make a note. Suppose that I flip coins and the probability of heads is 0.9. What's the most likely sequence of length n? All heads, right. And that has probability 0.9 to the n. Does that satisfy this? No. So the most likely sequence is not in the typical set. What about the least likely sequence? No, that doesn't satisfy this. That's here. But if you add up all these, the total probability is less than epsilon. So it didn't hurt us to throw away the most likely sequence. In fact, you can make a strong statement that says, you know, what's the smallest set that has a certain amount of probability, 1 minus epsilon? Well, to get the smallest such set, you definitely want to include the most likely, the next most likely, and so on, down to the ones that have, these are the ones that have roughly 90% ones in them. So we can define actually a set that's slightly smaller than A. But to first order in the exponent, it's the same size. So you can see that. I won't prove that right here. It's in the text again. So the size of the smallest set that contains 1 minus epsilon of the probability is to first order in the exponent 2 to the nh. So including these most likely sequences doesn't, it gives you the smallest such set, but it doesn't really change the number of elements in the set to first order in the exponent. All right, and we had 5 reasons for H, for the entropy. And they were 1, it arises in the AEP. 2, data compression consequence, and H bits suffice to describe X. 3, 2 to the H is the effective alphabet size. for a multinomial coefficient, n choose n1 through n sub m, is just the entropy of the vector, the ith component of which is n sub I over n. So there's immediate contact with combinatorics, and that's how Boltzmann came up with the entropy function in his work in 1890. All right, today entropy rates, not just entropy, but entropy per symbol, that's an entropy rate. We'll look at stationary processes, Markov processes, and look at walks on a graph, graph walks. As an example of a Markov chain. Okay, let's start off with some definitions. X of I from I equals 0 to infinity, or 1 to infinity, or minus infinity to infinity. Might as well include that. This is a indexed family of random variables. The index I we usually think of as a time index, but it could be a space index if you wish. So X sub I is just a random variable associated with the observation of the process at time I. Now associated with this is X super n, which is X1 through Xn. In other words, it's a block of random variables from 1 to n. Sometimes I'll write, well, in case I'll define it when I do, I'll put the lower and the upper where the block starts and stops. And there's also the notion of P of xn, which is the probability that this random string of length n equals this given sequence from the alphabet. Depth. Stationarity. Now I think you all know what it is. And it's defined again, so let me just be brief. Xi is stationary. If probability x1 to n equals, say, this sequence an, where this is in script xn, is equal to the probability that from 1 plus k to n plus k equals an for all n and all k.